So let's look at solving some initial value problems. I made reference to this in one of the first couple videos for this course, but this is where we're really going to look into what that means. So we might need to just get a general solution for your differential equation, but we might know something about the original curve that means that I can find what's called the particular solution. In that case, we would call that an initial value problem where you have initial conditions. Now, whatever derivative the nth order you are in, you can only do this if you know up to the n minus 1th derivatives values. For example, if you have y double prime, if you have a second order, then to solve this completely, you need to know both the y value at whatever initial value you're looking at and the y prime value there. Let's look at an example here. Let's show that y equals c to the x is a one-parameter family of solutions to y prime equals y. Well, the nice thing about exponential functions is their derivatives are the same thing. Therefore, when I plug in y prime and set it equal to y, that is what I get. So that's my verification. Now, if I want to find the particular solution that goes through 0, 3, what that means is because c can be anything, right? If c is positive, I'm going to have an exponential function like this. But if c is negative, then I might have an exponential function like that. So what I'm going to do is when x equals 0, y equals 3, that's going to go into my solution curve. E to the 0 is 1, so c must be 3. And if you do know things about exponential functions, it makes sense that if my exponential function has a y-intercept of 3, that 3 would be the constant in front. All right, let's look at one that might be a little more tricky. When x equals 1, y equals -2. So -2 equals c e to the 1. Well, e to the 1 is just a number, so I can divide by the number e on both sides, and I get c equals -2 over e, or -2 e to the -1. Therefore, when I plug that in, that's what I plug in for c. And I wrote it like this because even though plugging in this would be fine, I do want us to see that I could have -2 and then e to the x minus 1. If I multiply like bases, I can add their exponential powers. And so it is also okay to write the solution curve like this here. It is a little bit tricky for some solution curves because you can verify that both y equals 0 and y equals 1/16 x to the 4th both satisfy this differential equation under this initial condition. Meaning, if I were to solve this differential equation using the techniques that we will learn later in this class, I might have some different solutions I need to consider. And so sometimes graphing and knowing things about the situation will be really helpful for us to determine which one of those two solutions is the correct answer.